would like to ask Daniele to answer the last questions, because now we will then change the topic, so it's better to answer now. So please, Daniele.
Yeah, thank you, Danilo. So I ask it to answer to the question, because then Niccolò will change a little bit the topic. So I prefer to answer first before the lesson of Niccolò. So the question was, why is not easy to make a vulnerability map a regional scale? No, sorry, probably I was not so clear on this point. So it is not difficult to create a susceptibility map at regional scale. What is very hard to do at the regional scale is to create a risk map, because in risk map you have also to consider the vulnerability, and make a vulnerability at regional scale in many cases is not so easy, because you have to consider the degree of loss and to measure in terms also of money, or using different parameter, the entity of loss related to the effect of the slope instability at the regional scale. That is why a regional scale, in many cases, the final goal is a susceptibility map. On the contrary, a local scale, in many cases, we are able to obtain a risk analysis and obtain an evaluation of the risk assessment that we can reach using the definition of a scenario. So we have a landslide. We consider the volume of the landslide. We consider, for example, the runout of the landslide. That means that we are able to make a model of where the landslide could stop. And according to the area that could be involved in the landslide evolution, we are also able to make, for example, a risk assessment. So a definition of the vulnerability, considering the different elements of risk that are present in this area. That means that a local scale is quite easier to define a risk assessment than at general scale. So I hope that now I've been able to answer to this question. Sorry for the crash of my computer when I was answering to the question. If there are not many questions, I believe that we can move to the next presentation.
Okay, Daniele, thank you very much. Now I'm giving word to Niccolò Dematteis, who will continue the lecture. So Niccolò, please, you can share your screen.
Okay. Thank you, Danilo. I don't know if it is sharing the...
Yes, it's appearing now.
Okay. So good afternoon. I am Niccolò Dematteis. I am a colleague of Danilo and Daniele. My research mainly focuses on the use of remote sensing technique for monitoring glacier. And therefore, my lecture concerns a possible approach for monitoring glaciers, that is the use of time-lapse imagery. And in particular, I will show the application of this approach to monitor the PLANPINCIEUX glacier. Therefore, my presentation is divided into parts. The first one is more theoretical and describes the technique of digital image correlation. And in the second part, I will describe in detail the results of this monitoring concerning the Planpinicieux glacier kinematics and instabilities. What is digital image correlation? Is a technique that has been developed in the 80s for laboratory experiments, and since the beginning of this century has become to be used also for terrestrial monitoring of glacier. However, it is not many used, and continuous peak monitoring are rare, but for the Planpinicieux glacier where we are working on. The principle of DIC is to search for the displacement of a portion of taken from an image acquired at time 0 to search for the position of this tile in a second image acquired at time 1. And how can we do that? We can calculate a similarity index for every possible positions in the second image between the reference tile, that is the red airplane in this case, and every possible positions in the other image. Then we will obtain a matrix of similarity, and the positions where the maximum of this similarity corresponds to the movement, to the displacement of this tile. This operation is the spatial cross correlation. The cross correlation has can calculate unit displacement, but it is possible to achieve sub-pixel sensitivity using interpolating surface where we can search for the maximum and therefore obtaining sub-pixel sensitivity. However, in glaciological applications, the typical uncertainty of the digital image correlation is approximately one pixel. But I now want to present a typical application of this technique for glacier monitoring. In this case, typically it is acquired an image sequence of many images per day, but only 1 day of displacement is obtained every day. And I will show why just in a minute. The processing chain is usually composed of a series of steps that include the image selection, acquisition and selection of the images, some manipulation of the images to improve their quality, then the co-registration of the images, and the calculus of the cross correlation itself. But the most important step, I think that it is image selection. In fact, using bad quality images will result surely in bad quality results of displacement. So if we consider to have a reference image of good quality, it is important to use a second image with a similar illumination. This is because the presence of a different pattern of shadows can disturb the calculus and introduces errors in the results. And of course, it is mandatory that the scene, the process that we are monitoring is visible. Therefore, during night or during bad weather, this approach, monitoring approach, is not applicable. I said before that just one result per day is achieved with this technique. This is because we want to use images with similar illumination conditions, and therefore ideally acquired at the same hour. And also because the uncertainty of this method is so high that hourly measurements are often within the uncertainty values. The digital image cross correlation can be applied to monochromatic images. Therefore, common practice is to convert colored images in black and white tones, but it's also possible to use a single band. But usually the intensity of the image is the most common choice. Another important task is the co-registration. In fact, between two images, there can be a shift due to the vibration of the camera, and therefore it is possible to select a stable area, for example, a bedrock area, where to calculate the displacement of the two images, and then translate the images in order to compensate this displacement. Then the displacement of the process, in this case of the glacier, is calculated within a sliding window that covers all the image. And within each window, the cross correlation is calculated, and it is obtained a value of displacement. Therefore, the very output of the digital image correlation is a map, so a spatially distributed result of the displacement. But as you can see from this picture, digital image correlation provides two components of displacement. In particular, the two components orthogonal to the line of sight. Therefore, the output are two maps, one of the vertical component of the motion and the other one the horizontal component of the motion. The result of the cross correlation are in pixel units, but it is possible to apply a metric conversion using photogrammetric formula. For example, this photograph of the PLANPINCIEUX glacier, in this case, one pixel, the footprint of one pixel is approximately 5 centimeters. Then, in many situations, it is important to have represented the result in the real-world coordinates, and therefore the data must be georeferenced. In order to do that, it is possible to auto-rectify the image on a digital terrain model used as reference. And using this approach, it is possible to compare the results of the digital image correlation, or maybe couple this data with other monitoring devices. Digital image correlation is a valuable tool for glacier monitoring because it requires hardware that is very low cost and is easily portable. In fact, the very sensor is just a reflex camera. The results are maps, so spatially distributed displacement value of the two components of the displacement value. This is a quality of this technique, but it is also a constraint because we don't have any information about the displacement, the displacement component along the line of sight. This is a remote sensing measurement and this is important for glacier monitoring because very often glaciers are perilous to access in, or maybe it is impossible, and therefore the use of remote sensing sensors guarantees the safety of the researcher and technicians. Of course, this approach has some constraints. For example, it is impossible to use during night and bad weather, as I said before, and it suffers shadows effect, and therefore this direct solar illumination can alter the result. But the one limit is also that it is necessary to select the images to be processed, and this is usually conducted manually, and therefore human efforts are required to select the image. The sensibility of the measurement are quite low, but this is often irrelevant for glaciers because are fast processes, and therefore 1 pixel of uncertainty is sufficient to detect with the high precision and accuracy the glacier motion. Okay, now that I have presented the theoretical part, the monitoring technique, I will show a case study where this technique is applied. That is the PLANPINCIEUX glacier. This glacier is located in the Mont Blanc area in the northwestern Italy. It lies in the Italian side of the Grand Juras Massif, and in particular, it is in the Ferrer Valley, in the municipality of Courmayeur. The elevation of the PLANPINCIEUX glacier ranges between 2,500 and 3,500 meters, and therefore the accumulation area is partially cold-based, and it is composed of 2 circuits that merge in a plateau from which starts the ablation area that is in temperate thermal regime. What means temperate thermal regime? It means that there is presence of liquid water at the interface between bedrock and ice. Most of the glaciers in the Alps are temperate, or at least partially temperate, because the elevation in the European Alps are not so high. In the lobe in orographic right of the ablation area is the Montita lobe. It is quite steep, and its surface presents many crevasses. This lobe is of particular interest because the morphology of its terminus provokes an intense and frequent calving, because there is the terminus of this lobe ends in correspondence of a morphological step, and therefore the glacier cannot move beyond this morphological step, and it disintegrates in fragments that can be also of many thousand cubic meters, and that can be dangerous for the population. A small overview about the recent evolution of the glacier. In the last 20 years, as you can see, the glacier retreated, as like most of the other glaciers around the world. depending of the position of the front, it retreated between 100 and 300-400 meters. And it means a reduction of the area of the glacier. But not only the area reduced it, but also the... Oh, my computer... Okay. Also, the thickness of the ice reduced. In fact, the ablation area thinned of about 12 meters in average. Here, it is shown a depth of difference between the glacier elevation in 2014 and 2019. Globally, this means a volume lost of more than 2 millions of cubic meters. Okay. I have spoken about the Monti Talob. In the past, from this part of the glacier, several break-off of large dimension occurred, and in a few cases damaged the road and a bridge that is present in the bottom of the valley. Therefore, the authorities decided to activate a monitoring plan, and since 2013, it was activated a continuous monitoring using a time-lapse camera. This kind of monitoring allows at measuring the surface daily velocity of the glacier, but also the visual analysis of the pictures allows to identify the break-off and to evaluate the behavior of the glacier and the development of possible instability processes. This is the photographic monitoring station that is installed in the opposite side of the Ferre Valley in front of the PLANPINCIEUX glacier. The distance is almost 4 kilometers. The station is equipped with 2 reflex cameras with different focal length. In this way, it is possible to observe the glacier globally, and one camera focuses on the Montita globe, that is the very objective of this monitoring plan. As this station is energetically autonomous, thanks to the presence of a series of solar panels, it is remotely controlled with a GPRS connection. The system is controlled by a Raspberry Pi microcomputer, very cheap. And it is acquired 1 image per hour for each of the 2 cameras. A monitoring station like this one has a global cost of approximately 10,000 euro. This is not cheap, but if you consider that this station is active since 2013 and that it does not need a great maintenance, this system, I think, that can be considered low cost. For example, just to have an idea, since in 7 years of monitoring, this station acquired more than 35,000 of images. Most of them have been acquired in the warm period because in winter the solar panels are covered by snow. However, the main activity of the glacier occur in in summer. And during this period, we can observe the glacier evolution at high temporal resolution. So it is a very large data set. But what are the products of the monitoring? There are two main products. One is quantitative, and it is the digital image correlation provides it. That is the velocity of the glacier, the surface velocity, that can be observed as a surface map or of the time series of the velocity of a limited portion. And then there is the visual analysis of the pictures that provides a qualitative investigation of the processes and of the glacier behavior, and in particular the identification of the break-off and the observation of the opening of the crevasses, for example. This monitoring is conducted for research purposes, for sure, but also it serves for controlling the glacier behavior and for be sure that dangerous situation cannot occur. And therefore, daily update web page is shared with the authorities in order to have clear the situation of the glacier, and periodical bulletins serve as an in-depth analysis of the glacier development and its evolution. Okay, concerning the velocity of the glacier, here you can see the surface velocity map, the mean velocity between July and August since 2014. Very interesting observation is that the kinematic pattern of the surface is divided in different kinematic domains. What is a kinematic domain? It is an area characterized by uniform velocity. Therefore, this means that there is a gradient between different kinematic domains. But the interesting thing is that the limits of these domains correspond to the position of some crevasses. In the surface of the Monte Talob, every year, a series of crevasses open and delimit some morphological sector. The opening in every year in the same position means that probably the bedrock is not a flat slope, but it presents discontinuities, and the crevasses open where the tensile stresses are strongest. The fact that the kinematic domains correspond to the morphological sector is important, because just observing the results of the digital image correlation is possible to evaluate the most unstable portion and a first evaluation of their volume. In fact, since until 2018, there were 4 distinct kinematic domains, and the most unstable was the frontal one, the domain A, which usually had a volume of 50,000, maybe 100,000, that it is not a dangerous because probably collapse of this volume cannot reach the bottom of the valley. But in 2019 and in 2020, something different happened. In fact, the two lower domains, domain A and domain B, merged. There was no velocity gradient, and there was no large crevasse between these two domains. They formed a single morphological sector with a very large crevasse above that. And therefore, all these portions were very unstable. And in 2019, the volume was estimated in 250,000 cubic meters. And this summer, the volume was the double. And with a volume like that, a possible collapse could easily reach the bottom of the valley and damage the buildings and maybe threaten the safety of the population. Therefore, last year and this year, the authorities decided to close the access to the Ferre Valley for safety reasons, but fortunately, no large collapses occurred. Sorry, okay. These are the time series of velocity. This is the mean velocity of the frontal sector between 2014 and 2020. The black dots represent the break-off events, and the white circles, the dimension of the white circles is proportional to the dimension, the volume of the break-off. As you can see, every year, a few accelerations, strong accelerations occurred, and they culminated with a large break-off. But why there is such an acceleration? Because there are two displacements that act together. There is the sliding of the glacier, and when there is this acceleration, there is a portion, the frontal portion of the glacier that has a rotational movement. There is the toppling. If you remember, Daniele talked about this process in its lecture. This toppling occurs because there is a crevasse above this portion that develop, and when it reaches the bottom of the ice, when it reaches the bedrock, the ice chunk collapses. This is the process, the dynamics that describes this behavior of the velocity of the glacier. But also, we found that there is a monotonical relationship between the velocity and the volume of the break-off. Therefore, a higher velocity implies a larger volume of the possible break-off. And this is important because it allows to estimate the volume before the collapse. It is just, it is not very precise, this estimation, but it is important because the order of magnitude can be estimated. How it is possible to estimate the volume of a break-off using b-dimensional images such as the pictures? It is not simple, but during years of experience, we were able to define a series of assumptions about the geometry of the bedrock and of the ice, and we compared the results of the volume estimation using these assumptions with the LiDAR data, which are three-dimensional data, and we used them for reference, and we found a good agreement. And therefore, the uncertainty of this kind of estimation is quite large, but the accuracy is high. And this approach can be used also in different contexts. Of course, we identify all the break-off during the years. We estimate their volume. Here it is an example of a large collapse of, I think, approximately 10,000 cubic meters. It is very clear the area collapsed in the map of change detection. This is one possible approach to identify the collapses. But also, we try to analyze the processes that creates the break-off, and we found three classes of processes that provokes break-off of ice. The first one is the disaggregation. It is the most frequent, and it is just the disintegration of the frontal part because the glacier moves beyond this bedrock discontinuity, and therefore it disintegrates because there is no more any surface where to lie against. But this kind of collapse it has usually small volumes. On the other hand, a second process, that is the slab failure, has usually large volumes of ice involved. This is the detachment of an ice lamella caused by the development of a crevasse. And this is the process that often occurs when we observe the acceleration. In fact, this process is often preceded by an acceleration of the velocity. A third process is the water tunneling. This process is caused by the presence of water inside the glacier. The water sometimes can accumulate within the glacier, but the water do not discharge and creates water pockets, then can exert a strong pressure against the frontal wall, and they can this wall can collapse and create instabilities. But also the empty cavities can collapse themselves, and these two processes are linked to the presence or to a large content of water inside the glacier. But what makes the glacier move? We are measuring the motion of the glacier, but until now we do not think about the causes of this displacement. There are two main forcing. In winter, there is the gravity. The interface between bedrock and ice is freezed. There is no liquid water, and therefore only the gravity exerts is forcing, and the frontal part has a mass too low to overcomes the friction and therefore only the main body of the glacier moves. And the crevasses that open during the summer, in winter, close. In summer, during the warm season, the things are different. In fact, there is presence of liquid water that is caused by ice melting, and it arrives at the bedrock ice interface for percolation. Therefore, one can suppose that high temperature cause an increase of the ice melting and therefore an increase of the glacier velocity. And another thing that one can assess is that the presence of snow or the absence of crevasses that limit the water percolation can reduce the glacier sliding. The two things are true, but it is not so simple. In fact, observe the plot in the upper left corner. This is the positive degree day for every year since 2014. The positive degree day is the cumulative sum of the mean positive daily temperature. This line is the positive degree day index of 2014. And in fact, in this year, we did not observe acceleration, those speed up periods. And therefore, the temperature appears to be linked to the velocity. But if we observe the series of temperature and velocity in the subsequent years, we cannot detect, we cannot notice a clear relationship between these two variables, because often they appear in counterphase. In 2017, it seems to be some correspondence, but it is not a general rule. And furthermore, if you see the velocity of 2018, the velocity increased only since the end of the beginning of September, because probably since in 2018 the snow cover of the glacier lasted until the beginning of the August, the melting season started later, and therefore it is possible that the presence of snow causes a reduced glacier sliding. But in reality, the very forcing of the glacier motion is the hydraulic system. In fact, a well-developed hydraulic system facilitates the water drainage, and therefore the pressure, the basal pressure is lower and the friction is higher. On the contrary, if there are a lot of small channels or maybe film, this creates a strong pressure against the bedrock and reduce a lot the friction against the bedrock, and therefore the glacier can slide more easily. Also, the presence of cavities can increase the pressure, the internal pressure. Therefore, the presence of water, for sure, it is the most important element that can influence the glacier sliding, but it is important how the water is distributed within the glacier body. And it is important to monitor the water discharge, because the hydraulic system can change during the season, because the glacier moves and therefore the channels can change, can collapse, can create. And it is important to monitor the water discharge, because suppose that during a period of high temperature, we observe a limited water discharge. This can imply that there is an accumulation of water inside the glacier, and therefore the instability of the glacier increases. Yes, just to conclude my presentation, I have presented a possible approach to monitor glacier, that is the use of time-lapse imagery. In particular, the use of the digital image correlation allows at obtaining quantitative data about the glacier velocity. In the case of the PLANPINCIEUX glacier, we observed a relationship between the velocity of the glacier and the volume of the collapses, and even the strong velocity increase can be a precursor of large collapses. Therefore, this approach, this monitoring approach, is a valuable tool for risk assessment. Also, the analysis of the kinematic patterns is an indication of what can be the unstable portion of the glacier. But I want to remark that using this approach, it is not possible to predict the instant of the break-off. And also the temporal resolution of the data, that is a daily temporal resolution, is too coarse. And therefore, the digital image correlation and in general the time-lapse imagery cannot be used for early warning activities. So there are these two elements that have to be taken in account. Risk assessment, yes, but early warning, no. And these are two activities that is important to maintain separated. Okay, thank you for the attention, and
thank you. Thank you very much, Niccolò, for your presentation. And there is already a question. Are the images received online, real time, or is recorded on the system and requires to collect it?
The images are received in real time. The acquisition is scheduled every hour, and every hour we receive the images that has been acquired in this period. We some year we even did not reach the monitoring station. It is very autonomous and very robust. In 2020, we will go for a maintenance mission to the monitoring station only next week, just to give an idea.
Thank you so much. Are there any questions or comments? Okay. If not, I will suggest to have a 5 minutes break, and then we will start for this short presentation concerning the current event hitting our region in the weekend. So we'll see how an exceptional precipitation can affect the territory. Okay, I'm stopping now the registration. I'm thanking again Niccolò, and see you in 5 minutes.